By the early 1950s, the United States faced a new reality. The Soviet Union had successfully tested nuclear weapons and possessed long-range bombers capable of carrying those payloads directly over the Arctic. To track incoming flights, the military relied almost entirely on human calculations. Airmen used analog circular slide rules, like the Felsenthal whiz wheel, to estimate intercept angles and aircraft speeds. Tracking a target meant an observer had to radio coordinates to a central command post. There, operators stood behind large, transparent grid boards, writing the flight paths backward with grease pencils so officers on the other side could read them. A human plotting a course on a plastic board is no match for a jet traveling at 600 miles per hour. The delay between radar detection and command action left the continent effectively defenseless. In 1951, a computer was essentially a massive calculator. It didn't have a screen or a keyboard. Instead, operators interacted with the machine using stacks of perforated cardboard punch cards. This was batch processing. You loaded a problem in the evening, let the machine run overnight, and collected the results the next morning. The computer analyzed what had already happened, often hours after the fact. The Air Force needed something completely different. They required a system that could monitor the entire continental airspace, refresh that picture every second, and operate 24 hours a day without failing. Asking a machine from this era to process data instantly and continuously violated the basic logic of 1950s computing. Computers simply didn't communicate with the outside world in real time. To counter a sudden airborne attack, the military had to build a computing network that functioned continuously, a concept that didn't yet exist. The Semi-Automatic Ground Environment, or SAGE, relied on a central processing hub, the IBM AN-FSQ-7. These machines weighed 250 tons each. They drew up to 3 megawatts of electricity and were massive enough to require dedicated 4-story concrete bunkers equipped with their own cooling towers. To process data at a continental scale, the machine used over 55,000 fragile, glowing vacuum tubes arranged in dense, towering rows. To move information from the coast into the bunker, engineers established a vast communication web, transmitting live radar telemetry and weather data over thousands of standard analog telephone lines. This diagram outlines the flow of those inputs. You can see how long-range radars, picket ships, and airborne observers all stream their data down into the centralized computer. By continuously ingesting and parsing live telemetry from across North America, SAGE functioned as the world's first active, real-time database. If the machine went down during an attack, the resulting gap in coverage would be catastrophic. The system required a perfect, zero-downtime operational record. IBM achieved this through duplex redundancy. They built 2 complete 250-ton computers into every facility. One processed the live air picture, while the second remained on hot standby, continuously syncing data so it could take over instantly if the active machine failed. This real-time data had to be legible to human operators. Instead of reading punch card outputs, airmen looked at large cathode ray tubes, the first graphical user interface. To command a machine, an operator used a handheld light gun, aiming it directly at the screen to select a specific radar blip. Once a target was tagged, the computer automatically ran the interception algorithms. It calculated the necessary flight path and assigned the nearest fighter jets or missile batteries to intercept the threat. This interaction created a loop between raw processing power and human judgment. It was the first time people and machines worked together in a continuous, interactive ecosystem. At its operational peak in the 1960s, the network consisted of 24 direction centers, coordinating an unblinking 24/7 defense shield over North America. This project defined IBM's business for a generation. Between 1952 and 1955, SAGE contracts accounted for 80% of the company's computing revenue, providing the capital required to scale into a global technology leader. The project forced the development of technologies that are now standard: overlapping inputs and outputs, real-time processing, graphical displays, and distributed networking. If you map out the SAGE data loop, you are looking at the exact structure we use today. Data from edge devices travels across a network into a central server, which processes it and pushes it to a user interface. This model was used for the first direct commercial spin-off, Sabre. It applied the same real-time network architecture to revolutionize how airlines managed flight reservations. The SAGE defense network was eventually rendered obsolete as slow-moving bombers were replaced by intercontinental ballistic missiles. But the logic of its software survived. The attempt to build an impossible weapon outlasted its original military purpose. By proving that computers could exist in a continuous, networked state, IBM and MIT established the basic rules for the modern digital world.